Earth's magnetic field has been weakening at an accelerating rate, and 2025 satellite data reveals concerning changes in our planet's invisible protective shield. Scientists monitoring the magnetic field have documented a 15% decline over the past 200 years, with the rate of weakening tripling since 1980. This isn't the gradual, uniform decline researchers initially expected. Instead, specific regions are experiencing dramatic drops in magnetic field strength that have prompted intensified monitoring efforts worldwide. The South Atlantic Anomaly represents the most significant area of concern, stretching from Brazil to South Africa. This region has lost substantial magnetic field strength over the past 50 years, creating what scientists describe as a magnetic weak spot where charged particles from space can penetrate deeper into Earth's atmosphere. Satellites passing through this area regularly experience computer glitches and electronic failures when they encounter the compromised magnetic protection. The European Space Agency has documented magnetic field strength dropping significantly in this region, representing some of the fastest rates of magnetic field decline on record. Aircraft flying over regions with weakened magnetic fields now face increased radiation exposure, forcing airlines to adjust flight paths and limit crew flight hours to protect pilots and passengers. The aviation industry has implemented new protocols for routes that pass through areas where magnetic protection has diminished substantially. Flight crews working these routes receive enhanced radiation monitoring and modified scheduling to minimize their exposure to cosmic radiation that would normally be blocked by a stronger magnetic field. The technology systems across the globe face mounting challenges from magnetic field fluctuations. GPS satellites lose accuracy when operating in regions with compromised magnetic protection, leading to navigation errors that affect everything from smartphone mapping applications to precision agriculture systems. Power grids experience more frequent disruptions as geomagnetic storms become more intense without adequate magnetic shielding. Electrical infrastructure in affected areas suffers voltage fluctuations and transformer failures at rates significantly higher than regions with normal magnetic field strength. Communication networks encounter severe challenges during periods of magnetic field instability. Radio signals that normally bounce off the ionosphere get scattered and distorted when magnetic field irregularities disrupt the upper atmosphere's electromagnetic properties. Emergency communication systems for aviation and maritime operations experience blackouts during geomagnetic events that would have been manageable with stronger magnetic protection. Internet infrastructure relies on undersea cables that can suffer induced electrical currents from magnetic field fluctuations, causing widespread connectivity disruptions. The health implications of magnetic field weakening have become a growing concern for researchers studying radiation exposure patterns. People living in areas with significantly reduced magnetic field strength show elevated levels of cosmic radiation exposure, particularly airline crew members and frequent flyers who spend extended periods at high altitudes. The increased radiation exposure correlates with higher rates of certain health issues, though long-term implications continue to be studied through ongoing population health surveys. Animal species that depend on magnetic navigation for survival are already showing signs of distress from magnetic field changes. Sea turtles, which use magnetic field patterns to navigate across ocean basins during migrations, have been found stranded on beaches far from their normal routes. Migrating birds show increased disorientation and navigation errors, with some species arriving at breeding grounds weeks later than normal or failing to reach their destinations entirely. Whales and dolphins that rely on magnetic navigation for deep ocean travel have been stranding themselves more frequently in areas where magnetic field anomalies disrupt their natural compass systems. The disruption extends to smaller animals as well. Bees rely on magnetic field detection for navigation between their hives and food sources. Beekeepers in regions with significant magnetic field weakening report decreased honey production and increased colony collapse rates as bees struggle to navigate efficiently. Even bacteria that use magnetic particles for orientation show altered behavior patterns in areas where the magnetic field has weakened substantially. Scientists have deployed extensive monitoring networks to track magnetic field changes in real time. The European Space Agency's Swarm mission uses 3 satellites to create detailed maps of magnetic field variations across the globe. Ground-based magnetometers stationed at over 130 locations worldwide provide continuous monitoring of magnetic field fluctuations. This monitoring network can detect small magnetic field changes and provides early warning systems for space weather events that could damage satellites or disrupt power grids. Protective measures are being developed to shield critical infrastructure from magnetic field-related disruptions. Satellite manufacturers now install enhanced radiation shielding and backup systems specifically designed to function during magnetic field anomalies. Power grid operators are implementing surge protection systems and backup transformers in regions identified as high risk for geomagnetic disruption. Emergency communication networks are being hardened with protective shielding and redundant systems that can maintain operation during severe magnetic storms. The research community has established international cooperation programs to study magnetic field changes and develop coordinated response strategies. Scientists share real-time magnetic field data across national boundaries to create comprehensive global monitoring systems. Research teams collaborate on computer models that simulate magnetic field behavior and predict future changes. Emergency management agencies are developing response plans for scenarios involving severe magnetic field disruption. Computer models predicting future magnetic field behavior suggest that current trends could lead to significant changes in magnetic protection over the coming decades. The mathematical projections become increasingly uncertain beyond shorter timeframes because magnetic field behavior involves complex interactions between Earth's molten iron core and its rotation that scientists don't fully understand. These uncertainties make it difficult to predict exactly when and how magnetic field changes might affect different regions of the planet. While scientists work to understand the implications of our planet's changing magnetic field, the oceans beneath us harbor discoveries that challenge our understanding of life itself in ways that seem almost impossible to believe. The ocean's invisible alien forest. Deep beneath the ocean's surface, marine biologists in 2025 have discovered microbial communities that challenge our understanding of life in extreme environments. Recent research from Aalto University has revealed deep-sea microorganisms that produce complex sugar compounds in ways that shouldn't be possible under the crushing pressures and complete darkness of the ocean depths. These microscopic life forms have developed biochemical processes that operate efficiently in conditions that would destroy most known forms of life. The deep-sea sugar production mechanisms discovered by researchers involve bacterial communities that have evolved unique metabolic pathways. These microorganisms can synthesize complex carbohydrates without any access to sunlight, instead using chemical energy from hydrothermal vents and organic matter that drifts down from surface waters. The sugar compounds they produce are unlike anything found in surface-dwelling organisms with molecular structures that remain stable under extreme pressure and temperature conditions. Scientists studying these deep-sea microbial communities have found that they form intricate networks that span vast areas of the ocean floor. Individual bacterial colonies communicate through chemical signals that coordinate their sugar production activities across distances of several kilometers. This coordination allows the microbial communities to respond collectively to changes in nutrient availability and environmental conditions, creating what researchers describe as a distributed biological intelligence operating in the ocean depths. The sugar compounds produced by these deep-sea microorganisms serve multiple functions that extend far beyond simple energy storage. Some of these complex carbohydrates act as antifreeze agents that prevent ice crystal formation in the organism's cellular structures. Others function as pressure-resistant structural components that help maintain cellular integrity under crushing deep-sea conditions. The most unusual sugar compounds appear to serve as communication molecules that allow different bacterial species to coordinate their activities and share resources. Australian researchers have made equally remarkable discoveries about large marine organisms adapted to extreme deep-sea conditions. Giant isopods measuring over 20 inches in length have been found living at depths where the pressure exceeds 1,000 times at its sea level. These massive crustaceans have evolved specialized physiological adaptations that allow them to survive in environments that would instantly crush most surface-dwelling creatures. The giant isopods demonstrate remarkable metabolic adaptations that allow them to survive for months without food in the nutrient-poor deep-sea environment. Their digestive systems can process almost any organic matter that reaches the ocean depths, from dead fish and marine mammals to organic debris that sinks from surface waters. When food becomes available, these creatures can consume meals equivalent to several times their body weight and then enter extended periods of dormancy that can last over a year. The pressure adaptations of giant isopods involve specialized proteins that maintain their structural integrity under extreme conditions. Their cellular membranes contain unique lipid compositions that remain flexible at crushing pressures that would solidify the membranes of surface-dwelling organisms. The isopods' nervous systems operate through modified neurotransmitter pathways that function efficiently despite the extreme pressure environment. Deep-sea exploration has revealed that these extreme environments support biodiversity levels that rival surface ecosystems. The combination of chemical energy from hydrothermal vents, organic matter from surface waters, and specialized microbial communities creates complex food webs that support hundreds of species found nowhere else on Earth. Many of these deep-sea species have evolved bioluminescent capabilities that allow them to communicate and hunt in the complete darkness of the ocean depths. The metabolic processes of deep-sea organisms operate at efficiency levels that challenge our understanding of biochemistry. Some bacterial species can extract energy from chemical compounds that are toxic to surface-dwelling organisms, converting sulfur compounds and heavy metals into usable energy sources. These extreme metabolic capabilities suggest that life can adapt to conditions far more hostile than previously thought possible. Research teams have documented deep-sea organisms that can survive temperature fluctuations from near freezing to over 400 degrees Fahrenheit near hydrothermal vents. These temperature extremes occur within distances of just a few meters, requiring organisms to possess cellular mechanisms that can rapidly adjust to dramatic environmental changes. The proteins and enzymes that enable this temperature tolerance are being studied for potential applications in industrial processes and biotechnology. The discovery of complex sugar production in deep-sea microorganisms has implications for understanding how life might exist on other planets. The ability of these organisms to synthesize complex organic compounds using only chemical energy suggests that life could potentially exist in environments previously considered uninhabitable. Astrobiologists are studying these deep-sea metabolic processes as models for how life might function on planets with no access to solar energy. The interconnected nature of deep-sea ecosystems demonstrates how life can create complex relationships even in the most extreme environments. Bacterial communities provide chemical compounds that support larger organisms, while the waste products of giant isopods and other deep-sea creatures provide nutrients that fuel microbial growth. These symbiotic relationships create self-sustaining ecosystems that can persist in isolation from surface waters for extended periods. The chemical compounds produced by deep-sea organisms are attracting attention from pharmaceutical researchers seeking new sources of bioactive molecules. Many deep-sea bacteria produce antibiotics and other compounds that show promise for treating human diseases. Unique biochemical pathways that produce molecules with properties not found in surface-dwelling species. These discoveries about life in Earth's most extreme environments reveal how much we still don't understand about the biological processes operating around us.